biomass. We have trouble getting anything to work in this country on the biomass front, but they're really good over there. So you're privileged to have him lecturing you rather than Dave or I, who don't really know what we're talking about on this subject. So over to Björn.
Okay, thanks. I will be recording this lecture not because I spend my time navel gazing, but because I need to upgrade some of our distance learning lectures anyway. I'm Björn, I'm professor in bioenergy technology, basically specialized in combustion as such, but covering also the general field of bioenergy technology, supply systems, the fuel resources and so on. So we'll talk a little bit about bioenergy and biofuel. Basically, you know this very well, that the reason to use biofuel for energy is basically, of course, that carbon loops, so that biomass may be considered CO2 neutral. And this is illustrated by this infinity sign, where the important steps are the photosynthesis reaction, where CO2, carbon dioxide and water are taken up and form biomass, solid biomass, that might be summarized basically as CH2O. That's a very, very simplified description of the photosynthesis reaction. But what it says is that 30 grams of biomass from the photosynthesis reaction binds 467 kilojoules of solar energy. And that energy can then be released again from a combustion reaction where we take the solid biomass, oxygen from the air, and create carbon dioxide and water vapor, which goes back into the atmosphere and then loops around. Now, looking at biomass, some people would say that use of biomass for energy is a modern thing. Do you recognize that? That's the Colosseum in Rome. Now, to build that, there's a lot of brick and cement. All that brick and cement was produced using biomass fuel, basically wood fuel. The temperatures needed for that process is about 1,000 to 1,500 degrees. This is the mirror gallery in Versailles. The whole castle of Versailles is more than half a kilometer wide. It was built during the 1600s. All the glass, all the steel, all the mirrors, all the brass, all the cement, all the brick was produced in wood-fired furnaces, needing temperatures between 1,100 and 1,500 degrees. This is a cannon from a Swedish ancient warship, but same kind of cannons were used by Nelson at Trafalgar. Cast iron was produced in wood-fired furnaces at 12 to 1,600 degrees. So these are the kinds of temperatures that we can easily reach using biofuels. Now, what we call modern use of biofuel is basically concentrating on boiling water. For steam raising, we need a temperature between 500 and 800 degrees. So this is a very low qualitative process that we're using biomass for today. And especially in case we are talking district heating, for example. Then we only heat the water up to about 100 degrees, 120 degrees. Whereas the biomass fuels could be used for much more advanced processes than that. The most complicated thing we could ever figure is to try to get the trees into the tank of a car. That is absolutely the most complicated thing we could ever figure. It takes several step conversion processes. We lose energy. Every conversion is a loss of energy and a loss of efficiency. The total efficiency from tree to a car that is rolling is theoretically could be down at about 70%. In reality, we are today down at efficiencies about 40 to 50%. And that is what goes into the car engine. Now, the efficiency of a car engine is in itself about 30–40%. So you will realize that only 10% of the original biomass energy actually moves the car, which is amazing. This is absolutely the most complicated thing we could ever do, and is not what we would like to do in the first instance. Now, there's also, quite often, there is a confusion between what is biomass, what is bioenergy, and what is biofuel. And this conversion is clarified by looking at the Federal European Standard 14588, which was inaugurated in 2003. It's currently being updated together with a number of different standards for biofuel. In this standard, we clarified that we have biomass, which is the solid substance which is created by photosynthesis. Whether this solid substance is wood or is cotton, like this is biofuel, cotton, cellulose fibers, or is agricultural wastes or food scrapings or anything, that's biomass. The biomass can then be upgraded into a biofuel. Biofuels can be solid, liquid, or gaseous. So biofuels are not stuck or defined by their state of aggregation. A biofuel can be either solid or liquid or gaseous and still be a biofuel. This is not to be confused with bioenergy, which is electricity, heating, cooling, mechanical movement, pressure increases in a gas or anything. And to go from the fuel into bioenergy, there is the combustion process, which is the one and basically only process we have to extract the energy from the fuel and do something with the energy. Now there's a lot of different options, certainly. There are different types of biomasses with different characteristics. Fiber and cellulose-rich biomasses are often referred to as lignocellulose, that's woody biomass. That's lignin, cellulose, and hemicellulose. We have residuals and wastes, such as this guy here after it's been used, or my shirt, or your cotton clothes, or wool clothes, or whatever you have. We have the sugar and protein-rich stuff, which is typically agricultural residues. And these three main different groups of resources, they will suit different types of processes as a primary conversion or primary process. We might gasify the stuff, produce a synthesis gas, and that is applicable to lignocellulose, it's also applicable to residuals, and it's applicable to agricultural residues. Gasifying means that we lose some of the energy in the original biomass. We produce a synthesis gas, which is composed by carbon monoxide and hydrogen. Using carbon monoxide and hydrogen, we can then recombine and build up any hydrocarbon, basically. So we can produce methanol, for example, or dimethyl ether, a substitute diesel fuel for cars, or basically anything. We could also use the gas directly in a combined heat and power production or a combined cycle power plant. And we can use it directly in industrial processes, if we feel like that, for steel or glass or something else manufactured. We could also use direct combustion to produce heat, and I've indicated that with thicker arrows because this is the most common and most high efficient route to go. Direct combustion can then be used for steam raising in a combined heat and power plant or for district heating. It can also be used for industrial processes like steel and glass manufacturing or brick and cement manufacturing. We can use the agricultural residues and sewage sludge, for example, in biochemical conversion, fermentation or digestion into alcohols that could be used for car fuels, or biogas that is also an alternative for car fuel. Trying to go from cellulose-rich biomass into fermentation and digestion is something that is looked at, but the problem is that cellulose cannot be digested. So first it has to be converted into simpler sugars. So it's a several-step process to get lignocellulose into biogas and ethanol. So the thickness of the arrows here slightly indicate what can be done, what are the most direct and logical routes to go. Looking then a little bit at what we need. This is a map from 2007 of the carbon dioxide emissions from the European Federation, split into sectors. You will notice that the biggest sector here is the production of electricity and heat. Second biggest is road transportation, but then comes manufacturing and construction. We have the residential sector, which needs heating. We have iron and steel production, 4% of the total. We have cement production, 2%. So the last decade, there's been a concentration on trying to get biomass into cars. But if we look at the total emissions from Europe, the carbon dioxide emissions from cars is not the dominating sector. And it's also the most complicated thing we can try to do is to get the biomass into the cars. So what we should do if we want to make an impact is to concentrate on this sector, this sector, this sector, and then some of the industrial sectors, such as cement and steel. And not look so much into the production of car fuels. And that means that if we take away the car fuels from this scheme, you will notice that this route becomes less interesting from a total point of view. Locally, in an agricultural region, this will of course be important, but from a full European point of view, this is not the main route to go to get lower carbon dioxide emissions. This is best useful in case we actually want to convert the fuel into something new. If we want to take solid biomass and turn it into a gas like hydrogen or a liquid like methanol, then we have to go that way. But if we have a solid biofuel, solid biomass, and we only want to get heat, then there's no reason to go via gasification. It's only complicating things. It's only lowering the total efficiency. So if we take away the car fuels, then there's actually no real reason to go via gasification at all. And the direct combustion route comes out as even more important if we really want to make an impact on carbon dioxide emissions. Now, the combustion process is slightly tricky because it is turbulent. That means that mixing is random. Sometimes gases mix, sometimes they do not mix. Combustion is a chemical reaction, so it needs time. And that means that if we have a certain combustion volume and we want to increase the load, then the residence time for the gases in the volume will decrease. And sooner or later we will hit the limit where the combustion reactions cannot run to completion. And that will then create a lot of emissions. It's temperature dependent like any other chemical reaction. So if we have a combustion unit with modulating control so that the load can change continuously within an interval, then what happens is that when we are at maximum load, we have the shortest possible residence time, and there might be too short time for the chemical reactions to run to completion. At low load, we might end up with too low temperature, so that the chemical reactions are too slow, and we hit a lot of emissions again. And in between, the mixing between gases, that is air and combustible gases from the fuel, is depending on the kinetic energy of the gases. We need mixing energy to tumble them around and mix them with each other. Now, kinetic energy is proportional to the square of the velocity. So basically that means that if we go down to half load, we get only 25% of the kinetic energy, and the mixing becomes very bad. The combustion process is the one that is responsible for all the emissions that we are creating in or from combustion plants. Even though a biofuel is considered carbon dioxide neutral, it may well emit a lot of unburned hydrocarbons, it may well emit a lot of particulates, it may well emit a lot of nitrogen oxides. And all these are created during the combustion process. So there's a combination of choice of fuel, choice of combustion equipment, and limiting the load range that makes the combustion process environmentally friendly. So to make this actually environmentally friendly, it's not enough to choose using biofuel. Also, the fuel must be based on a sustainable resource. Not all biomass is sustainable. The fuel must be produced in an environmentally friendly way. It's quite possible to produce biofuel using so much artificial fertilizer that the total life cycle analysis shows that it's not sustainable or not environmentally friendly. It must be stored and handled in an environmentally friendly way. For example, if you have a big storage of wood chips, what happens is that they start decomposing. They will emit bad smell. They might auto-ignite and cause a fire. Or they might deteriorate so that basically you don't have any fuel left. So there can be lots of problems with the storage. That has to be taken care of. The fuel must be combusted in suitable combustion equipment so as not to create a lot of hydrocarbons, particulates, and bad air quality. And that's a tricky part. And finally, the ashes from the combustion unit should be recycled back to the soil again, because the ashes contain a lot of the nutrients. So these nutrients should be recycled back to the soil. Otherwise, what we are doing is that we are taking away nutrients from the soil, finally reducing the soil productivity. Now, looking then at the resources, I don't know if, did you think that the world is big and round? more or less spherical. Did you believe that? Well, it's not. The world is small and flat. Actually, if we split the land area of this world equal between everybody living on it, we today get 3.2 football fields of land each. 3.2. This says 3.5, and that is because it's calculated on 6 billion people. Today we are about 7 billion. Do you know the geography? What's on these football fields? Give me a hint. I'll trigger your fantasy. One of them is completely unproductive. That's hot and cold deserts, the Sahara, the Arctica, Antarctica, high mountains like the Andes, the Alps, things like that. So that's one football field. What's the second football field?
The ocean.
Huh?
Sea. The ocean.
No, this is land area.
Okay. All land area.
No water on it. Second one is forested. There are basically three types of forests on this planet. It's the boreal forest, the taiga region. It's the temperate forest where you live. The taiga forest is where I live. And it's the tropical forest. These are basically the three main ones. What's on the next football field?
Plains, grassland.
Pardon?
Grassland, plains.
Yeah. Meager grassland. That's Central Asia, that's the savannas of Africa, etc. This grassland carries enough grass to also carry a sheep, or a goat, or a yak, or something, but not a cow. So you can't grow hamburgers on this. You can grow woolen carpets on it. That works fine. But you can't grow clothes, you cannot grow hamburgers. You cannot grow food, cereals and stuff. So we're left with half a football field. What's on that?
Fertile grassland. Fertile grassland.
That is this part. Fertile grassland. That's where we can grow hamburgers. Okay? Good enough to grow hamburgers and grass. It's not good enough to grow cereals and bread. It's not good enough to grow cotton. So you can't grow clothes on it. You can grow hamburgers though, because it's good enough for grazing. This is where we shall grow all our clothes, all our remaining food, bread and all that stuff shall grow here. Some people think that we should use that land also to produce fuel. I say no. I say we should grow food and fiber on that, but not fuel. We need clothes, we need to eat. And that's all the land we have to grow food and fiber. So looking at the world from that perspective, you will realize that the wooden residual fossils, that is the main biomass resource. And looking at Europe, looking at a map of Europe, you'll notice that there is actually forest all over the place. It's not very dense in many places, but it is there. There's also, of course, agricultural residues from different areas, like olive stones from here, like, I don't know what kind of residuals you have here, maybe some straw or something that can be used, or maybe if you have a crop rotational scheme, every 4th year you can grow some kind of an energy crop. That could be useful. There's oil press cakes that can be used from these countries that produce quite a lot of oil plants of different kinds, sunflowers, for example. The oil press cakes after you've extracted the sunflower oil can be used for fuel, but there shouldn't be any dedicated agricultural crops grown for it. But basically, the lignocellulose is the main resource. So we go back to these things. We took away the car fuels previously, looking at the actual emissions from Europe, and noticed that the actual emissions from Europe were from electricity production, from industrial processes, and from domestic heating. So that reduced the amount of output that we actually need in Europe. Now we've had a look at the resources, and we found that this is the main resource that is available. So finally, the best way to go is basically this. There's some logic to that, isn't it? So let's then look at how can we get such a system working. Well, you have the resource, you know which resource to look for. And what you need is then an effective infrastructure to take that resource from where it is growing and upgrade it into a biofuel. So take the biomass and turn it into a biofuel. That could be chipping and drying, or it could be sieving, or it could be just collecting and baling, or it could be lots of different processes depending on what is your regional resource. Then you need to get that fuel from the upgrading place into the final consumption place, that is the energy plant. And to do that, you will need to have transports, you will need to have intermediate storages. And that will need a supply chain infrastructure to be built up and established. Otherwise, it won't work. Then you will have the final use, the combustion plants basically, and the distribution of the energy, the use of the energy from the combustion plant. Whether that is a district heating network or it's a combined heat and power plant, so a district heating network and a connection to the electric grid, or if it is a district cooling system so that you have a combustion plant producing hot water, putting the hot water into an absorption heat pump and distributing the cold water, or whatever kind of plant you have. But you need that infrastructure. Now, this final end user can be different types. It can be a process industry, steelwork. It can be a municipal electricity or energy plant, or it can be an individual household. The individual household will only dare to go for biofuel provided that the two first structures are in place. Suppose that you have a house. Suppose that it's midwinter, so there's a risk for frost. You want to go to the Canaries for a week. Now, if you cannot trust that the energy system is reliable, you dare leaving your house risking that the water pipes would freeze because of a lack of fuel? No, you wouldn't. So you would, in that case, not go for a biofuel system because it wouldn't be reliable. So to get this in place, you simply have to have these two established. Otherwise, no one will dare investing into a local biofuel system, will they? Now, So let's have a look. This is an extreme example. You can't read this, but the idea is to give you a graphic impression. These numbers are a bit old. They show the Swedish woody biomass flows in 2003. Why 2003? Well, because what happened in the winter between 2003 and 2004, January 2004 actually, was that there was a storm that overnight knocked down a whole year's felling worth of trees in Sweden. So that obstructed the Swedish woody biomass flows for a period of about 10 years. The last of these storm fellings was actually put into the sawmills only recently, only like last month or so. But this is a normal situation in Sweden. The idea is just to show you what happens. We harvest around 100 million cubic meters of wood in Sweden every year. Part of these 100 million cubic meters is left in the forest. And that's around 20 million cubic meters. And about 80 million cubic meters are brought out as timber. The timber is split into two main streams. 50% goes to sawmills, 50% goes to pulp and paper. When 1 cubic meter of timber comes into a sawmill, only half a cubic meter actually comes out as sawn goods. The remaining remaining volume becomes sawdust and shavings. So it's about 50% that comes out as sawn goods, which is exported and imported as an international trade. What goes to paper and pulp industry comes out as paper and pulp, which are exported and consumed in Sweden. Actually, the wood industry is the economic backbone of Sweden. It's the industry sector that creates the greatest net income to Sweden as a country. But at the same time, this produces fuel. And fuel and energy is becoming an increasing part of the business for sawmills, for paper mills, for pulp mills. So the byproducts, the sawdust from the sawmills is turned into pellets and briquettes. There's also an internal use of sawdust and cutter shavings and things, and bark and wet chips. There's internal use of the black liquor, of the chips, of the bark in the paper and pulp mills. The residuals that were previously left in the forest are nowadays taken out, extracted, and used as fuel chips, a little bit also as fuel wood. And we've also got the waste recirculation system into reasonably working conditions in Sweden, so that quite a lot of the waste is also used actually for energy. That means that ultimately this shirt will come back as electricity and district heating someplace. I don't know exactly where. Probably Ljungby, because they are the ones that currently take most of our waste, but maybe some other place. And that is an important observation, that you can then use wood as a fuel and also use the same wood for furniture, for paper, by recirculating the final waste. So if take down a tree, you make a table for IKEA of that tree. That table is sold, it's used. The sawdust during the production of the table is used for energy. The table is used for eating on, until it becomes unfashionable. It's thrown out. It's chipped down and turned into kraft paper, which is used for packing eggs, which is again recycled, used for packing electronics, and again recycled and comes back as fuel, as electricity and heating. So the same wood can be used several times. The important observation, and what I want you to remember, is that biofuel does not have to be virgin. It has to be clean, yes, but it doesn't have to be virgin. Biofuel can be wood that has been recycled 5 times for different purposes over its life. It's still biofuel. Okay? That's a very important observation. And that is the mistake that people often do. They think that biofuel has to be virgin, and they forget that there's a lot of wood in the world. So then the conclusion becomes biofuel is something that has to be grown on fertile agricultural land. Sorry, that's the wrong conclusion. And hopefully you will never ever draw that conclusion after this lecture, okay? Now, this biofuel, for example, this stuff here, in pellets, can be used locally in individual houses, like with a commercial pellet stove. Now, unfortunately, this stove is 15-year-old, and we've had a very cold winter. So I did some repairs to it. This is our own. I did some repairs to it, and it's currently getting just on the edge of having to be thrown out. So I just bought a new one, but I haven't installed the new one, so this is a picture of the old one. Now, this is an on-off automatic unit. It heats air. It works as the high load unit in our home. Base load unit is this one, a hot water boiler, which heats the house and produces tap water until the temperature, the outdoor temperature, is about 0 to -3, roughly. Then this pellet stove comes in, and since this is automatic, goes on-off control. It only runs when it's needed. Then it keeps the house warm until it's like -10, -15, and then we have to go into woodlog firing, manual woodlog firing when it's colder than that. But that's not very many days per year. The point is that this kind of equipment is commercial, provided that the private customer in this region knows where to buy pellets and can buy pellets. Then this is a real alternative for house heating. But if the pellet supply is a bit shaky, if you cannot be sure that you can actually buy wood pellets on that day when it's cold weather, then you would not trust such a piece of equipment, because if you can't fuel it, if you can't put the fuel into it, then you can't use it. So we're coming back to the need of an infrastructure. Now, you can use wood pellets for high temperature applications if you feel like it. I happen to live in that part of Sweden where the glassworks, the most famous glassworks like Kosta and Boda and Ågefors and all these, the Swedish crystal comes from. So the nearest glasswork is 800 meters away from where we live. We retrofitted a glass melting furnace at Kosta Glassworks a few years ago. from our university department, just to show that it works fine, because people tend not to think that you can use biofuel in industrial processes. Now, this is art glass, so it's very clear glass, it's top quality glass, and it was no problem with the glass quality. The automatic control system was not too difficult to adopt to run on pellet firing. So it's not a big technical problem to reintroduce biofuel into high temperature industrial applications. The technology is basically on the shelf. The total system, no, that's in the wrong place. If you go into larger buildings, like university, these kind of buildings, then you need a larger boiler, and there would be boilers commercially available in the size suitable for this kind of buildings. They can run on pellets, and in the larger scale they can run on wood chips. Of course, the installation requires that there's a separate boiler room that can be set aside in the building. That's necessary. It also requires that you have basically a water-borne central heating system. That is the most simple thing to control. Airborne heating is more complicated to control. Going further up the scale, when we're talking a smaller municipality, say 500 households to 1,000 households, then we would be talking small district heating networks. Again, this type of boiler it's not a standard boiler. It's not so that you can call up the boiler manufacturer and say, hey, I need a 1 megawatt wet wood chips district heating boiler delivered tomorrow. They will say, unfortunately, we make them to order. But we will immediately start making it for you. Whereas if you want a pellet stove, you basically go into the pellet stove shop and say, hey, I need that one. Okay, take it. Well, you have to pay. But these kind of boilers, they are made to order. So it takes a little time, but it's a standard construction. There's nothing fancy about it. If you don't have a chance to build a boiler, you already have some kind of a district heating system, and you want to introduce biofuel to build up and establish the fuel production infrastructure and the fuel supply infrastructure, then go for co-firing. Probably you will have, if you have a district heating system someplace, there would probably be a waste incinerator someplace in the system. Co-firing wood chips with waste is excellent. No problem at all. Definitely no problem. So that is the easiest way to start establishing the infrastructure of fuel production, fuel supply. If you don't have district heating at all, maybe you only have electricity production. Well, co-fire biofuel with coal in the large electricity production units. Again, this is no problem. Up to about 10-15% of the total energy can easily be replaced by biofuel. Again, the idea being to establish the fuel production infrastructure and the fuel supply infrastructure without having to invest anything. It's a question of getting fuel producers up and running. It's a question of getting fuel to be a natural thing, to say, hey, I need 20 tons of biofuel delivered tomorrow, please. And they say, okay, 20 tons. So it's a question of getting the systems running before the systems can diffuse into the small scale where people are dependent on a stable and reliable supply. So basically, except for the fact that we need biofuel as one way to combat global warming, the use of biofuel will also add value to agriculture by giving another option to treat some of the residues or side products. It can add jobs, local opportunities, because it takes handling, it takes harvesting, it takes production and infrastructure to be handled. And that creates local jobs which are long-term sustainable and local income from taxes. It's a part solution to the waste problem. Waste deposits are growing all over Europe, and we need to recirculate what can be recirculated and use what is clean for the energy system. This is part of the solution to that. But it needs then an integrated view from the planners so that politicians, planners, business work together in the same line, and not anyone wants to create their own little reserve in this. It's not one group's business, it's a societal business. So now for a little bit of advertisement, but that can be there while floor is open for 2 minutes, 3 minutes for questions. I'm sorry, I had a little overshot of slides, but there's time for a few short questions. Just shout, just shout.
Like when you use natural gas, if it's accidentally leaked before it gets to when you use it, it causes pollution in the air. When you create the gaseous form of the fuel,
Shout higher.
When you create the gaseous form of the fuel, if it's accidentally leaked in the transport to the production, is that any impact on the environment?
What happens, there's two different routes basically to create a gaseous fuel. It's the thermochemical way, which goes via gasification, and it's the biochemical way, which goes via, for example, anaerobic digestion. Now, if there's a leak from the anaerobic digester, what happens is that methane gas comes out. If there's a problem with the thermal gasification, what happens is that the total efficiency goes down, which means that you have to take out more raw material. So if something goes wrong, there's definitely an impact to the environment. In both cases, what happens is that if you would only need the energy in the far end, then like heat or so on, then the total efficiency would be lower than going the direct route. But if from a thermal gasification plant, now there's the risk you take if there's a leak or a problem, a process problem, is that heavy hydrocarbons, like tar hydrocarbons that are carcinogenic, might come out in the atmosphere. And from anaerobic digestion, it's mainly methane that is the problem. Anything else? Yes, just shout. Shout high.
Say the idea really took off, and pellets were provided everywhere, and really used and utilised these boilers. We need to plant a lot more trees to then use for the wood pellets. Was there enough at the moment? What would the effects be on ecosystems as well?
The trick is that wood pellets have so high density and are processed so that they can be internationally traded. So, for example, if you want to import wood chips to the UK, you can't do it from Canada because of pests and pesticides and parasites that might be with the wood chips. But wood pellets is not a problem. So, and also the total transport life cycle, if you do a complete carbon dioxide analysis for the total life cycle, including sea transport, it's still very, very positive. So it's not a big problem to import like wood pellets, because here in the UK you wouldn't have space to grow all the trees needed. Like in Sweden we produce 1.5 million tons of wood pellets per annum. 25% of the total energy in Sweden comes from biofuel. Only part of that is of course from pellets. But so you can buy some pellets from us, you can buy from Estonia, Lithuania, Finland, you can buy from the Baltic region, you can buy from Canada. There's a big international trade with pellets. So it wouldn't be a big problem.
What would be the CO2 impact of, say, like the extensive use of wood pellets?
Put it this way, whichever energy carrier you're talking about, if you're talking gasoline, if you're talking electricity, if you're talking wood pellets, whichever, when you get 1 kilowatt hour to yourself as an end user, between 5 and 15% of that energy, so 0.1 plus minus 0.05 kilowatt hours, has been used to get it to you. And you can assume that that has created CO2 emissions. And this is similar for any energy carrier. This is the same for all energy carriers. Now, if it's a fossil energy carrier, like gasoline, then finally, when you use it, you also create even more carbon dioxide. If it was a wood pellet energy carrier I bought here, then I do not net create any more carbon dioxide, but there was only the 0.15 kilowatt hours to get it to me that created the emissions. They are a bit anxious to get in out there. And since we were a bit anxious to get in with the previous group, maybe we have to give up.